Okay, so what are we covering today will be leading on deep learning, will be the next session of the family with recurrent neural network, right? So that's something that we will hope to explore. How is it different from traditional convolutional layers? How does it deal with sequence data? So one key difference between the two of them, I hope everyone can see my slides, okay, also. If any issues, do flag out, okay, in the chat or raise questions along the way, right? So one thing, as you can see, for those they may have some, again, biology experience or even not, right? CNN is almost like glucose. As you can see, the standard of the structure of the network is roughly quite standard. Whereas the ones where we are talking about like RNN, it comes in all shape and size. So on the left, the diagram below is the most fundamental kind of gates that RNN works. So data comes in with X of t. So this is basically xt, right? This is basically xt minus 1. So the previous data with the new data coming in, activation function again, which is like tangent, was sort of controls the result that is relevant and useful for the data. On the right, you see other variants such as, okay, key of LSTM and GRU. Okay, so for LSTM, it stands for long short-term memory. That is one very common models that we use for RNN network. Okay, GRU is basically gated recurrent, meaning there's some special gates to regulate the data. And you can see from image, there's some forget output gate. What it all means later when we go into details is that it will transform the data into the right shapes and sizes that is useful and helpful for learning. All right. So the main takeaway here is switch your mind to RNN, right? Which is showing how the data is different from other traditional data like CNN, which deal with image. So that's a key things to it. All right. So next, going forward is where a key thing about RNN, because we deal with sequence data. So what's the sequence data, right? Things like audio, things like a video, there's a time pattern to it, right? Things like even for finance, stock prices, property prices over time. You can see all this data doesn't follow the kind of static image there is. All right, so that's the kind of sequential data we are talking about when we are looking for using RNN to solve, right? The most basic block of it is a single cell, not so much of a neuron or layer, but it does work in similar fashion. You are taking the input data and doing a combination such as multiplication and addition, right? So that should be a key we are trying to do from the hidden state. So every time the data comes in, we call it a hidden state, right? That's a vector that we try to progress, okay? To form a final vector. So vector is like just a data output, right? So you can imagine your data output having a series of values and rows and columns, right? It could be a series of, like I say, sound. It could be speech, the frequency of a speech. If it's a time series data, like prices, it could be a series of prices from 30 days ago till today, right? So those are the few straightforward differences we are looking at, okay, for the time series data. And then the new vector that you finally calculated, you will pass on to the next cell. So you can see that just now when the xt comes in, xt minus 1, right? When you join them together through the function, you go into a new state. A new state will go forward. So that's how you are doing. The hidden state is memorizing the data from the past. Okay, what CNN couldn't do, remember that if you look through any CNN tutorials, you realize that it doesn't sort of remember over time. It more of captures spatial features, right? So RNN captures more of a time feature. So that's something to take note, which is pretty different. All right. Okay, so you can see, just for those that have not see the graphical, right, you can see the HT minus 1 and the XT, the old data and the new data is currently joined on the left into the function, output into the new neuron, right? Then you will pass on next. So that's how the series goes for as long as it needs to be, right? So in more specific terms, just for your understanding, is the first time series that you are coming in, the X, okay, you are trying to predict Y1 for the current time, right? At the same time, using that, you will calculate the hidden vector, also called the memory for the next time. H2 is time 2, right? Then when you move on to, let's say this was yesterday, this is today, okay? Today comes in, you will realize that today will influence H2 again. So sort of you update H2, which is a vector, right? Okay, and change the memory of the data, and you predict the new variable, the new value for today, and you start to calculate the next day again. So you are updating the internal memory, right? Each time a new observation is being observed. So that is the main goal of what we are considering as the RNN memory power, right? If you blow this up to the whole process, you should be seeing that essentially this is a series of neurons, vectors coming in, right? You can see time data, let's assume 3 features, X1, X2, and X3, right? They're entering, so they are passing over time. Okay, so a sequence of data one by one, okay, store the memory of the previous thing. If you see the difference now, the interesting thing about RNN that is mentioned different from CNN, right? Okay, for recurrent neural network, what is essentially different is that the network comes in all shapes and sizes, not just in terms of the cell, but even in terms of the main architecture. Is one-to-one, right? So one-to-one can be a lot of very straightforward problems. So I want to predict tomorrow price, okay, with yesterday price, for example, right? Okay, one-to-many can be things like generating music. So we talk about a Deep Composer, right? Which is a product that has been, okay, yeah, changed, right? So by creating music, the image captioning, you send a full image and then you just want to summarize the image, right? So that's also a way of one-to-many. So one image generate a few texts. So that's one very common problem. Other kinds of problems like many-to-one can be things like a classification. You give a series of features, okay, could be a series of transactions of a person, and you predict whether this person is key customers or not. So that's also one very important way to do so. Right, so that's a lot of differences. A key few things are translation, which is like grammar, right? English to Chinese, to Mandarin, right? Tamil to Malay, for those who are near Southeast Asia, etc. You have translation, right? So for example, your name, I am whoever, you translate to another language. So that's many to many. Other kinds can also be autonomous driving and video recognition. So the use case of RNN may in essence seems to be much more in variety compared to CNN. But that's not to say that it is definitely the only model to use, right? Okay. And because it all comes in shape and sizes, it really needs to customize your data. So if you follow the pre-trained models, okay, like CNN, for RNN, you have things like transformers, GPT. They are very different, right? But they are all dealing with text data. So those are some things to take note. Especially in forecasting, right? So what's forecasting? I'm trying to predict the future, right? So you can check out DeepAR by AWS algorithm. The forecast unit as well does cover that. It fundamentally uses our LSTM type of architecture. So what is that, right? So we will go deeper into a long short-term memory. So you can see there are many interesting other cells that are doing something to control the flow of information. So obviously a forget gate is deciding what data to forget, what data to remember, okay? And control the data that is coming in, right? Okay. Next is one reason why we need this long short-term memory. Again, replicate your way of thinking, right? If you remember, you should as a person have some long-term memory of things. You remember your general upbringing, how you grew up from young to old, but you may not remember the exact events, to not every single exact event, right? So you have some short-term memory, right? In that sometimes the current data you should prioritize more, or you tend to forget a very recent event, right? And it goes into your long-term memory in more generic form. So hence, it's very challenging if a neural network starts to carry information, right? Imagine you start from today and you try to predict 1 year later. 1 year later, you will have to process 365 days of data points, right? It's not a light year. That's actually very extensive and computational heavy. So actually what you want to do is you want to drop some data along the days, right? Those that are not significant. Those that are more recent, you might want to prioritize them. So that comes into the field of deciding what to drop, what to keep, right? So hence that is where long short-term memories was first developed by giving some gates that do specific computation and functions. So this will be one family of RNN that are looking to go further deeper for the content per se, right? Before we look at some generic applications. Okay. So once the forget gate, how does it do and know what's droppable, right? So what you can see is this. You can see that the data is coming in and there's a 0 to 1. Why? The y-axis is 1, the lowest is 0. So you take the data which is 5, 0.1 and negative 0.5, right? You can see that now it becomes 99, 0.99, right? 0.52 and 0.00. So the last one is almost close to 0. So think about it, right? If anything multiplied by something that's almost 0 is basically forgotten, right? Those that are multiplied by 1 is just remembering its own data. So the way you sort of forget data mathematically is to turn it to 0. The way you keep the data is to sort of multiply close to 1. Okay, so this is the key to how we decide what to forget. The model will train the weights and make that decision, but that's how the forget gate starts. All right, so knowing the content helps when you are planning the abstraction of the model itself. Okay, so that's the key of that. Now, if you look at then going forward, what are other gates? So imagine the current data, meaning today, comes into the input gate, okay, where the input is taking in the data, the current data input and the previous hidden state, right? So the previous hidden state always remembers past data points, right? So you are both, you can see that it's going in the bottom picture, right? You can see that both is going into two functions. So one is going to the red color one, which is sigmoid function, right? Which is 0 to 1. If you recall from the slide just before this, when you multiply 0 to 1, you will basically mean 0 will be the things that you drop, 1 will be the things that you kept, right? Tangent, on the other hand, will turn it into a sort of negative and positive weights, right? So tangent goes from -1 to 1 for this scenario, right? So in this case, you will start to deprioritize certain weights and strengthen weights of certain features. So that's why the concept of, say, short-term data may matters more than long-term data intuitively can take place in the network. So when you multiply the tangent outputs with the sigma output, as you can see, when the data from today and previous data are both going into two different functions, they will have to join at the end together, right? They have to join in, all right, at the last cross here, right? When they join, they sort of decides at the end what is kept, and even if it's kept, right? If -1 to 1, you multiply by 1 is the same value, you decide whether it's a positive weight or negative weight. The priority of the features will change. So that's something that we consider a lot when we say gates regulate and sort of attenuate the feature, right, or transform the features. So so you can take note that forget gates go in the first layer. So if this is a LSTM network, right? Okay, just one LSTM layer, you can see how it works is simply the xt and the ht minus 1 will go into one forget gate, and forget gate will come here first. At the same time, the same data will go into another decision to compare whether the new data, how strong is it? Okay, then you have to join them again, right? So after the forget gate, okay, and the input gate, you can see they finally calculate a new cell state, right? A new memory of the data, right? So you multiply by the forget gate, you get to the final output. So output is going all the way to the right already, right? So that's the key, okay? When you find, another thing you do is pass into another tangent function, okay? Output data and previous hidden states, okay, are passed through, okay? So you have a new hidden state of the memory and also a new cell state, okay? So that's the goal of this key. So if you have to build LSTM by from scratch, right? Instead of using an API, okay, what you will do is simply take a forget gate that decides what data to drop, input gate that decides what data to add from the current time, right? And also an output gate that decides the next hidden state for the next time period. In the function on the right, that's what you're seeing, right? You have to take in the previous self state, previous hidden state. So previous self state is the previous data point, right? And then the self state was the memory of the past data. Okay, input, combine them together, have a forget gate, choose the data that you want to prioritize, multiply together, finally output into the layer that you are predicting. So that should complete one LSTM node. Usually you don't necessarily have to develop this from scratch. If you do using Python codes, you can simply change the formulas, right? You can possibly even add a weightage, for example, on the combined layer. So that's some customization that you can do if you are trying for that. Okay, so without further ado, we can take a look at, okay, so, okay. So looking at how you can use RNN, right? So let's look at some examples and illustrations. So if on the question of like what service you need, right? Usually deep learning, you will require some kinds of, okay, GPUs due to the nature of the data, which is a graphical processing unit. You can call it from the cloud. You can use instance in the case of AWS. You can use higher P2 or P3 or even a larger space is fine enough. Okay, or like instead of a M2, right? You can do a higher size. The GPUs is just like having more core processor of the CPU, so it calculates faster. Then other than the speed of calculation, you also have to be concerned about the space of the data. So text data usually is pretty huge, so that's something that you will want to be careful about, and that's something to take note, and hence that's also another consideration. Otherwise, also about the framework, if the framework they use depends on whether you are PyTorch, TensorFlow, or even Keras, or which Keras, those are some considerations that will be important. All right, so that's something to look. Now, let's look at a very easy Keras example first, okay, before we go into PyTorch, right? Okay, in terms of the abstraction of code. So let's say I'm doing a sentiment analysis. So what's a sentiment analysis, right? As we mentioned before, RNN has many types. So this is the case where it's like many to one, many strings of words predicting emotions, right? So that's the goal we are trying to get to. So with that, we are trying to do whether it's positive, negative, or neutral sentiments. So the data is coming from, you can check out this problem, right? It's basically 20,000 kind of tweets to train the sentiments, okay? So it's a very common use case that is very basic for sentiment analysis, all right? Other few libraries, because you are dealing with text, right? So you have to process text data. So just because it's text data, you can get some libraries like word cloud, okay? GenSim or Spacey, right? They are libraries to mine data from inside like visualizations, okay, codifying, tokenizing the data, okay, and even Spacey is a library for like stock words, etc. that we can look at, okay. So I hope that the screen is already enlarged sufficiently for you guys. So just let me know if there's any other issue or questions, okay. Also, just remember, right, you should change your kernel, which is the engine, to for this it should be TensorFlow, and it makes a difference whether using 2 or 1, right? So if you depreciate it, some codes are not able to work. So that's the issues, right? So import some libraries common. I'm just summarizing it. Like re is for regular expression, right? The most basic way to process text is using like literally searching for the words itself, the characters, etc. Drawing a graph, okay, NLTK is a library, okay, that has a lot of key information about how to process text, right? We are not so much covering text processing here, but it's definitely one important step. Just like when you deal with CNN, your image processing, you have that. Same for RNN, you have text processing if you are dealing with text data. Okay, so key things is stop words is words that you do not want to analyze. It could be just those filler words, right? Like a lot of times when people speak, they can say yeah. So these kind of things, especially due to local language, you can drop it. Okay, so the methodization, right, means the methodizer is to change the word back to the base word. So for example, I'm eating. Eating, the base word is eat, right? Okay, on my I have slept. So slept, the base word is sleep. So you are changing that. So those are a few things that you go in and launch it, right? Okay, so the data is basically a CSV file. This is data extracted from Twitter, right? To extract data from Twitter, you can use API or you can use scripting. In this case, it's just using a competition data set. So you can easily access that and play with it, right? Okay, so you can see the text is here. So these are what people have tweeted. This is selected text that you have sort of removed, right? Okay, you're only taking a few keywords like my boss is bullying me. You use selected text just to be bullying me, okay, negative. So that should be a key of how you are doing. Okay, can son of the 4-letter words, you can think of it yourself, 4 stars, right? Up to you. Okay, can. So total data set is 27,000, that's the length. Sentiments, there are always 3 kinds, right? Positive, negative, or neutral. Do count, you can see positive and negative is quite balanced and quite close. The neutral one is the one that is more higher, quite significant higher, but neutral is also harder to predict, right? One thing about deep learning is the challenge of subjectivity. You might think that a phrase is negative, someone else might not think that way. So that's something that we might want to take into consideration, okay? So it's hard for even humans to decide, right? Sometimes the machine is taking harder. So next is just to select the text, sentiment, and then look at it. Find any null values there is. So simply fill it with no content. All right, so this is what you are doing, right? So there will be no more null value after you've done that. All right, okay, you can just check it again, right? So let's do this. And so now it's 0 because we have sort of removed the thing. Okay, now there must be some data cleaning. Just a recap that deep learning, you have to clean it. Deep learning is a lot of unstructured data. This is almost like a whole lecture on its own. We won't go so deep into that for specifically here, but just take note of the importance of it. So some common thing you have to do with text is like remove URL, changing text into sort of a token, or you can think of it like a number or encrypted values, right? Remove things like emails, all these that are not that relevant to predicting sentiments, okay, also lowercase, etc., right? Okay, so this is what you are trying to do. Okay, finding URL pattern, okay, you are trying to change that, remove the email. Re is the library you imported, right? You import re, right? So that's the regular expression library that you use to search the data, right? To sort of clean it. Okay, you don't do it, your accuracy will be terrible, right? These steps are even more important sometimes than the model itself. So remove any new line, which is like /n or /s, right? Remove single quotes, etc. So finally return the data. When you have the temp, you will do the selected test, okay? You change it to a list, so you have sort of clean it up, all right? Now, this kind of sons of a 4-star, right? You shouldn't drop it. I mean, it's still important. I mean, although you don't know what's the star, but you sort of can infer that if you watch enough shows about people scolding one another, you should sort of guess what these 4 stars can be. But hence, you should keep it, right? You shouldn't drop stars, okay? Or any symbols that might highlight frustration, anger, or anything else, okay? Next is you have to tokenize the sometimes in words, right? So as this is a phrase, this is a sentence. You have to convert into each of it as one word. So you split it into words, okay? Then tokenize the text, okay, and sometimes join it just to ensure that you can get back the same. So tokenize and detokenize is for you to fact check that you have sort of be able to get back the same phrase, right? Like so sad, bullying me. Okay, neutral class 0, negative class 1, positive class 2. So that's how it works. Why Okay, so here I'm using Keras. So Keras is the easier version to use, right? It's the most straightforward for now. You just need to do categorical. It will do one hot encoding for you. Then you have three. Then you can delete the Y. That's the labels. So you can actually get the length of the labels. All right. So you can check what is the labels. Okay. Yeah. So it's a one hot encoding issue. Okay. Now, so you have to pad the data. We implement a tokenizer, right, and pad the sequence method to transform the text data, right, into a matrix array. So remember, every row is a statement, right? So every row has a few words. These words may not appear in other words. So in essence, when you do a one hot encoding on all the words, you're actually expanding the size of the data. Okay, it can be, each sentence can have different numbers to represent different words that is being used. It could also be repeated words in different rows. So hence the same token, also called the same number, can be repeated. Okay, and hence you will set the max words that you will process and the max length that you will process, right? So max words is in this entire data set, no matter how many words you can find in the entire 20,000 tweets that people have ever mentioned, you only look at 5,000, the highest count, right? More of the time. Don't forget that, as we already covered, sort of, you just need to rewatch the previous sessions, right? Deep learning, you have things like the optimizer, okay, which was stochastic gradient descent, which is common. There was also added. Okay, now there's root mean square props, right, etc. IMS, right? There's also processing text of a tokenizer, a sequence that pad the sequence. So why do we pad the sequence, right? Because every sentence is of different length. As you can clearly tell, different sentences are of different length, right? This is 3 words, this is 2 words, this is 4 words, right? At the end, your data that you put in the model has to be of the same length for every sentence, right? So for those that are of nothing, you just put 0, 0. That's why you see so many zeros, right? Which is pretty big. Now, why is deep learning a big challenge? It can be up to 27,000 of records with 200. Why 200? The max length of the sentence is 200 words, right? So you're going to keep it to 200. And the tokenized words can be maximum, the values can be up to 5,000. Okay. So tokenizer number of words will be the max words that can fit on the text, the data, convert the text to a sequence. This data size is already considered pretty huge if you check the memory that it takes up. So hence, the more data you do for especially text data, the more computational resource you should cater for. All right, so think about that if necessary. So train test split the data, okay, into X train, Y train, test as well, right? Okay, so you can test around with multiple recurrent neural network. Okay, first you can start with LSTM layer, right? Okay, and achieve good results. Okay, when the data set is small. Okay, you can even start with, remember LSTM is a family of RNN, right? So before LSTM, there's even more straightforward RNN. Okay, but usually you might think that it's too simple or accuracy. You should try, right? Now, also RNN comes in all shapes and sizes, right? So that's the key message of now. So you can realize that you can have this thing called bidirectional LSTM, right? Which is 2 ways of predicting the data, right? So it's sort of fact checking each other in terms of the text classification. Okay, so here I will show you how that you can also solve this problem using a convolutional 1D network, right? Because it's not a 2D image, it's a 1D data, right? So so that's something good. Okay, so this is how you can get the simple RNN model, right? Again, if you want to try that as a base case. Otherwise, this is the LSTM that you should start with first. So you can see that, right? For the RNN, you just have to set a sequential. So sequential is the module under Keras where you build the layers sequentially, right? Which means you add layers after layers. So first you add an embedding. Okay, remember you are dealing with data, right? So you put next was 5,000. Output is basically this, right? Okay, 20. Then you add LSTM, okay, with 15, okay, gates and drop out of 50% of the data. Then you add a normal final convolution layer 3. Why is it 3 at the end? Because this is a final dense layer, right? A fully connected dense layer. So a fully connected lens layer is basically your normal neuron, right? Which is this. Then you just have to put all the data into it, right? Okay. So this will be three because you have positive, negative, and neutral. And activation softmax is the probability, right? Okay, of the each classes. So that is the goal that you are trying to set. Okay, so that is basically how straightforward you can build the Keras LSTM model if you are using that layers. So 15 is the 15 unit, right? The gated units as mentioned. These are not just the parameters, right? If you just read out on LSTM, you can set the activation function here, which is equal to tangent, okay, or any other things that we saw in the concept of tangent, right? You can also have whether you want to have bias, etc. So there are many parameters. Okay, so 15 units is you saw in the lecture there are many gauge, right? Okay, so that's how you think of that as 15 units. Okay, yeah. After that, compile the optimizer this. Okay, again it's a multi-class, so same as your other CNN, right? You use categorical cross entropy. Metrics that you measure to compare model is accuracy. Okay, it does takes very long to train, so yeah, so it can go. Now you can change the epoch, right? So that's about 5. Okay, you see that every epoch takes about 16 seconds, right? So if you do 70, you can think of it like 15 times 70 is about a few minutes, right? So that's the key, right? So you might want to calculate whether you need 70 epoch for the example here, or you can do with less. Okay, so a lot of times you remember you can do a early stopping, right? So to run finish 70 is actually about 20 minutes, right? You can see whether accuracy has sort of improved. Not much already, right? So actually you don't need 70. Okay? Yeah. May not need, right? So you do an early stopping. Okay? If you are cool with that, you add that parameter. Otherwise, that is fine. Let it train. Okay, I only show 5 just for demonstration purpose, so it should be running. And then the accuracy is 55. You can have a hunch guess that going forward, right? Even if you finish 4 episodes, it should be about 5 range. So a single LSTM is in a sense not that great, right? Okay. Now next is version 2 is where you use almost the same thing. Okay. Right. The layers now you have one more bidirectional. That's the only difference, right? This is LSTM. So this bidirectional as you put LSTM, right, with 60% dropout and 20, and then you feed into here. If you want to compare, you can change this all to 5, right? And then this to 5 just to be sure, okay? Validation accuracy as well to sort of compare and monitor, save the best version into a file, right? The file is in HTF5. You can save it in other format like picker, okay, etc. Okay, picker files, okay? So compile using RMS props, which is the optimizing algorithm. Category should be, this is for the various clusters, right? Right. So metrics, etc. The only things you change this compared to what has improved. So that is basically a bidirectional. Okay, you can see that the accuracy has sort of improved for the validation. What this means is that you're actually predicting the generalized data quite well. So these models are less overfitted, which in a way is not a bad thing, right? Okay, so that's something to think. Okay, now how is this different from the base RNN, right? So you can look at it, right? So the base RNN is using a simple RNN. So all these different layers, right, just need to search on Kaggle, do some research, right? You can find the documentation, different layers, embedding, simple RNN, so etc. Right? So this is where you can have the key of changing the data itself. Right? So to turn in the data for the tokens, right, into a vectors of a certain size. Okay, that's the goal of it. All right, the dimension output is 15. That's why 15 goes into here 15. All right, so simple RNN. So that's the key. So the different layers are just doing. Remember, RNN don't necessarily have a forget gate. It just have an activation function. So that's the key difference. Whereas LSTM, you have forget gate, etc. All right. Next, what about convolutional 1D, right? Okay, let's say this. Okay, So convolution is now you see that using Keras, right? It's convolution 1D. If you recall from PyTorch, the language syntax seems to be almost similar. Okay, so again, embedding, because there's words here that you're using, right? Output of dimension of 40 for this case. Okay, input length is max length. Okay, so the output may be 40, but when you go to the next layer, 40 will be aggregated into 2, right? So it's 26. All these can be changed. Remember, the more neurons you extract, more features from the data, right? Okay, so that's something to take note. Okay, can. Then after that, I mass pool. Okay, the data. Okay, convolutional. Okay, max pool convolutional again. Then global max pooling, right? Okay, then optimizer same, the rest is different. So the only difference here is you are using CNN, and CNN, because they're convolutional, in this case it's not 2D, right? It's 1D. So of course for one single vector, right? Not a three-dimensional data. The data is only two-dimensional, so that's sufficient. Also, you have like global max pooling, okay, instead of just a max pooling. So there are some global max pooling means you pool the entire vector, right? Max pooling pool the regions of the data only. All right, so take note of that. Okay, all these you can easily search on the key if you require to figure out more about each layer. Okay, so what you can do is you may not be a masters of all these immediately, right? So you just do this, yeah, or you check through all the layers APIs, right? So there are many that you can select. So go into all the functions, etc. Right? So we covered 1D, right? We also covered LSTM, simple RNN. You can definitely read out more if you so choose to use Keras as your architecture. All right, or so-called the language for you to write your deep learning models. Okay. So after you have done it, let's say you can load it. It's still training, right? So I'm just going to go forward and show you the done results. Otherwise, we'll be waiting here for it to train. So test loss and test accuracy. Best model evaluate. Okay, that's about the, okay, out of all the models, the bidirectional is the best so far. Right? You can see convolutional is about 0.8, right? Whereas here is 0.89. Okay, and yeah, 8.4, okay, which is still better, right? Slightly. But the train accuracy is 8.9. Here the train accuracy is 9. Okay, so convolutional is overfitted. Okay, so based on validation accuracy, you should pick the bidirectional one. Okay, so recall that deep learning always overfit the data by a lot, especially convolutional data. So you might not want so much overfitting, right? That's one key thing. Next up, also take note that one key problem of deep learning is training time can be long. So that is a key thing to consider, right? If you are in a competition and you are not having enough time or even credits, so got time computational resource. Next is print out convolution metrics just to check. You can see for most of them, they are pretty good in classifications, right? About 0.8. So there's a bit of a false prediction, right, somewhere. Okay, so the false positive is basically 0.039 plus 0.016, about 0.045. Then the neutral is about 0.0. So actually there's more false positive than false negative. So overly predicted tweets to be very happy when it's actually not. So that's where it might go into, if you want to improve this data, you might think about language, right? Sometimes you can actually mean very terrible by saying things in a very nice way. Okay? Wow, you are so damn smart, right? It can actually means you are not good, right? So these are the nuances that we want to help the model to learn. So is there any way we can improve this data, both on the data side and on the model side, which I think can be recapped from the previous session. You can just feel free to previous sessions, right? Just review on that. Next, sentiments, the score is quite poor, okay, and you haven't also gone through hyperparameter tuning, right? So this is where you try to change the sequence and the tokenization. So that's really what we want to do. Okay, and finally, if you are comfortable, you just, if you want to use this and deploy in a SageMaker, right, you have to save it in JSON, okay, serialize it again, the weights of the model. Remember, every deep learning network has weights for all the neurons, right? You can just save it in weights, okay, or you can even use a picker for the tokenizer as well. right? To remember the tokenizer there. So that is basically the key of how you can do a quick keras. So that should be one of the more straightforward model itself. All right, so don't forget your batch size, all these are important as well, okay, the neurons as well, okay, and other parameters that you can tune, okay. Next. Now, let's say I want to move from text to other data. Is that possible? The answer is yes, right? So let's say I want to do a speech classification. These three notebooks are not, I don't think I can share over the Zoom chat after this at the end. So just remind me on that. All right. So the speech classification, right, is now turning the data from text to speech. Okay, so it's still within the field of linguistic, but just now that we're doing it with another data type, which is cool and fun. Okay, so that's something that we can explore, right? Okay. Next is what is a speech, right? So you must understand. So a speech is a sound, like audio sound, right? So audio sound has more data than just a text. Okay, if you convert my speech to another data format, you can get the sound, the amplitude, right, the loudness, the tone, the frequency, the pitch level, etc. So there are definitely more features. Okay, so I won't go into sound processing. No matter what unstructured data you deal with, right, you have to take into consideration that there are some processing steps very unique to that. That's the very core method of deep learning, right? So that's the key. One kind of common method we want to do is we do a frequency kind of extraction of the features from the raw audio files. Okay. Here I'm using LSTM just like just now, right? Okay, which is a type of recurrent neural network. So I install some tools and Python libraries to help me, like okay, like scikit-learn, etc. Okay. So after I get the data, this is an audio class you can play. So this audio class is saying that it sounds backward, right? So when someone say backward, this is the audio class that sort of predict that. All right. Then the raw data will be going through a few augmentation again. Let's take note of that, right? Okay. This key will be essential, like padding zeros. Okay, sometimes you pad in order to keep the length the same again. Okay, amplify the sound or change the speed. So this is some codes that you can use to augment the data. Now, this problem is a different problem. It's just speech classification. So literally, you hear audio sound, you know whether the person said 1, 2, 3, or 4. So it's a different problem from sentiment analysis. It's another use case. All right. Okay. So classifying of speech, almost like classifying of image, right? Just that now you are dealing with audio files. So you can see audio files literally are can be very noisy. Okay, so you have to do some augmentation, right? So after you augment, you can change it. Okay, so you augment the backward noise with some background like a C or even with echo. Actually, echo is a very good and important augmentation that we might want to do. Okay, and so now one thing to note is, right, if you transform the audio, you look at this, right? You think about this is almost like an image, right? This image, can you do CNN on it? Convolution, the answer is yes. So actually for speech classification, there are two ways, right? One is using RNN, one is using CNN. So they are interchangeable, okay? CNN will be more of doing it like image data, trying to find the patterns of the image in terms of the wave, how big is it, okay, how fast is it, etc. For RNN, is actually taking the features of the sound directly, right? Okay, like the time series pattern. So remember, RNN is more for sequence data. Okay, so let's focus more in RNN itself. So we saw a Keras version that might be much easier for most people. In fact, Keras is definitely should be more easy for most people, right? Because Keras is sort of like a wrapper around TensorFlow. Now here I will just use Torch for the discussion. Okay, so if you use Torch, right, we are going to have this RNN. Now, by now you should understand the architecture of writing a model using PyTorch. Right? So you have a class that tells you whether this can be any name that you like, right? Always initiate the features of this model. You have a hidden layers, right? Hidden size, how many units there are, how many layers there is. LSTM under neurons, right? Network for RN under PyTorch, right? You can call LSTM, which you have to put in the input size, the hidden size, and the number of layers that you want. Okay. Yeah. Then the linear is the final with the number of class. So there are sort of 11 class here, if I recall correctly. But regardless, it's 10 class, right? So you will have to change this in the final output, right? Okay, the hidden size is, remember the hidden vector we talked about over just now. So that's where you will decide on that. Okay, how many hidden size to look at and include. So device is basically whether do you have GPU or not. So that's not really critical. So batch size is basically the size of data that you have set already. Hidden state, cell state, start with all zeros, right? The zeros will be with the layers, with the batch size, okay, and with the hidden size, okay? Finally, you will have a LSTM model network to push the data. So this is why understanding this is useful. So this is the most raw version of how I build an LSTM without using a package. Okay? If I have to build it from raw, I need the previous cell state, the previous hidden state, okay, and the input of today, right? So these two are the key that I will put into the parameter, and I will have a forget layer, hidden underdate layer, multiply together and add. So this builds the foundation for basically your dish, right? You can see it's almost very synonymous. The current data that you're putting it in the original H0 and C0 that you are having. All right, so you forward propagate it. Okay. Now, finally, you output the last one, which is the linear layer, right? Which is FC, right? Fully connected. That will come out with number of clusters. All right. Okay. So that's the key. Now, okay. So just to make sure you are aware what's the difference with H0 and C0, right? Okay, so C0 is basically helping you to remember a longer term data. All right, so this for longer term. Okay, this for shorter term data. That's why you see the H0 multiplying with the, so short-term term can be last 30 days, right? Long term can be the entire data set. So that's just the key difference here. All right, so take note of that. Wait, to get a long short-term memory. Epoch 25 learning rate. Okay, remember this is a very key parameter, right? Okay, processing, you just have to run it. Then at the end, you can predict the clusters, whether it's right or left or audio class. So that's how you build the model itself. Again, if you want to save this to a file and then load on SageMaker or even deploy it on Lambda, right? That's the same process is save it to a picker file or H5 file, regardless, whichever is suitable for you. Save the weights, okay, as well, so that you can load both the weights and the. In this case, it's not text, so you do not save the tokenizer. Tokenizer is like an encrypted versions to memorize each text is which number, right? Here you are not dealing with text, so you are avoiding, you don't necessarily have that. All right, so that sums up the RNN. Now, a quick one on another use case would be using LSTM again, you can do genre feature data, right? Generation. So you can generate a sound. So you can see most of the model is the same. You still have input dimension again, hidden dimension, batch size that you want, and the numbers of layers. LSTM is set up input dimension, which is the data coming in from this layer, hidden state that you would have, okay, to learn, and the number of layers, right? Output layer will be a final output dimension that you get. All right, so passing forward will be one LSTM. So actually, usually you have one LSTM, but the LSTM is summarizing a full stack of how many layers you already have. Unlike CNN, right, if you remember convolutional 2D, you have to state it very clearly. One layer of convolutional 1D, one layer of max pooling, one layer of convolution to 1D. LSTM, it in essence means there's a 15 layers of the data already. All right, so take note of that. All right, okay. Now, so key of that, you will have the input dimension, okay, log softmax is in this example Adam, okay, and then finally you train and predict the validation, right? So accuracy goes up significantly. So this model you should keep training further, right? Now there's only 24, so you should go further because you can see strike improvement in the accuracy. Okay, this is a generation problem, so don't forget that you still can use your precision recall metrics for this. All right, so process the data, okay, turn it into a tensor format, right? Since it's PyTorch, okay, convert from NumPy to a tensor format, then build the neural network yourself. Accuracy is basically calculating how many is correct, right? Then you sum up all the correct prediction out of the entire data set. So number of training examples per iteration. They're supposed to have 400, but I only ran it for 20 times. So that's about it, right? You can run it longer if you want. All right, so that's something to take note. Okay, if this hope there's you are clear. If no questions, if there is, feel free to drop it in the chat for further discussion. Now, so again, as you can see, building your own network can be challenging, right? So let's look at some services that might help. Okay, and also bring your attention to how deep learning is so broad, right? Especially in the field of text data or even speech data. Okay, so one example is Transcribe, which you should know by what it means, right? It's basically generating text from speech, right? So speech to text. Usually, it's almost like just now the example I showed you RNN on speech classification, okay, or word recognition, or even language. Basically, it's or audio, right? Recognition. So all these are the different forms. Okay, so how you can use Transcribe is simply, for example, using some kind of video transcription service, right? Okay, by that. Okay, so let's say you have someone who is speaking and you want to transcribe this, right, to pick the right versions. Okay, so as the video process, you are trying to transcribe the video. Okay, so that is a key that you are doing. So this is just a general solution overflow. You don't have to follow exactly, but Transcribe is being used to take the data and convert into text. Okay, if you are going to build your own bespoke model like just now, that would mean you are doing a transcription problem, right? So you are taking audio data, like what just now you are doing for the speech classification, but now you are having to do it real time, right? Like every video of every word that's being spoken, you are trying to predict. So it's basically like speech classification on steroids. So you just have to repeat this speech classification many times, right? For every single word that is being produced. Okay? And if it's exact, then you can combine the entire sentence again. This is the most rudimentary way. Other way will be many-to-many models. All right. Yeah, is that if there's more than one speaker, you can actually segment based on the speaker. So that is one thing that the service can do. You can also build a model to identify the speech, the accent, the tone that is spoken by people. Right. The pre-trained models for these are not so common. You just have to do some research on that. Okay. The thing about RNN is that every single problem, right, has a very specific pre-trained models for it. Okay, because it comes all in shapes and sizes. Unlike image classification, right? You realize for image classification, the convolutional layers are many versions. You have VGG, ResNet, EfficientNet. When you come to here, the only most famous one is Hugging Face. I think it was brought up. Okay. That is quite a common one. Other than that, there's new versions like GPT, etc. Those are for translation problems. Okay. Of course, you can reconfigure the network and do other problems as well. Okay. This I won't be showing so much of using sort of augmented intelligence. So augmented intelligence is like getting a human to come and help training, right? So even if you use a service that is off the shelf, like AWS service, right, you still have to do some human training actually, essentially, right, to really enhance the results. But that's not a core component here. So just get the SageMaker, right? Okay, get the results, load it, right? The client will be using Transcribe, right? Also, if you are doing augmentation, you get the executions, okay? Upload the sample video to S3, right? Which is the video title, okay? And the file name and how is it used. So basically transcribe the video, okay? and process it, right? So here is just one example. Okay. Now to use Transcribe, we have to send a job like calling any normal job to AWS, right? So you have to give the job a name. Okay, so I'm just using my S3 path. The folder is demo, right? So my job names, I will append the stage video and one. That's about it, right? So this is the video I'm going to transcribe at the current time. Okay, the time is now, right? So now could be a current time. So that should be it. Okay, I think this one I can run it, see if it should work. Okay. Okay. Here is just to search the folder. It's not anything that is of significance, right? You just have to find the transcribe folder, okay, and print the number of videos if there is. All right. Now, you have to have a transcribe function, right, which is to sort of get the job name that you have created just now, okay, the URL of the job. Every job after you've transcribed the file, there's an output bucket, right? So you get an output bucket, okay, and the format is MP4. Vocab name is any custom vocabulary you use, right, that you feed the model. So not just finding who has spoken, but you can give custom vocabulary words, right? So if nothing, otherwise, if there is, you have to put your vocabulary name here. That's the only settings that is different. Otherwise, everything is just like language, English, or bucket, okay? Transcription job. So after the job is done, it will print out where is it, okay? And the content of it. Okay, so submitting a job means you get to the service, wait for the service to finish, right? Then you just have to get, okay, and so that should be something to take note. All right, I think this is done, yeah. Okay, yeah. So I can let you run for real time, but I'll continue explain first, right? Okay, so you retrieve and get the transcription results after you are done, okay? Just remember now the transcription results is stored in the job name in the JSON file, right? So you just have to retrieve from your bucket, okay? And get the buckets, okay, get the body, read the file, decode it to the UTF, okay? Print out the sentence, the confidence, okay? Every predictions has a confidence level, right? Also got accuracy level that you're comfortable with. So just set the function to print out like the punctuations, etc. If it's a new sentence, save the time, right? Okay, always add the words and scores and predict it, okay? And that's the function that you're trying to. So what you return from this function is the entire full transcript of the entire video, okay? The sentences that is being spoken and the times they are being spoken, the confidence. So every prediction comes with a confidence, right? Okay, and the final score, right? So that's the key to take notes of that. All right, so start time, end time, content, and the confidence. The list of confidence scores is called the score. That's it, right? So that should be what it returns. Okay, just need to find the bucket name and file name after it's done. Right, so that's what you do this. You may not need to build such a nice function to connect to the service, but you can do so just to simplify your work, right? Okay, so that's key. After that, you will pass run it, okay, pour the video in, get the data, right? So start time is this, end time is this. So the person spoke 0.54, right? 54 to 2 seconds, end time. So 2 seconds, hi, my name is Emily. So confidence is 553, right? So imagine one is this. You can, for one, you can print out the whole the range, right? Okay, and then save the full transcripts. Okay, if you have a distribution of all the confidence that because it's a video, right? So you are predicting what is being said at every point in time. Most of this, for this example, is pretty high, about 0.95, about that range. So actually, it's quite robust and stable. All right, so that's something that you should look at. Okay. If you find that any scores are less than, same for your model training, right? This is less of deep learning, it's a lot of post-diagnostic. You can actually filter it based on the threshold, right? So if it's less than the threshold, you just filter it, okay? And it should drop off. So there are 9 words that have less confidence, that is not very clear. So actually, in essence, you are doing speech classification, right? What I showed you just now using RNN is almost essentially the same. You are predicting whether is it 1, 2, 3, 4 are being spoken. The only advantage is if you have to train your own transcription model, you might need some heavy resource because you have so many words to transcribe, right? In this entire universe of words. And if you use a service, it can be much better, right? Because you access the corpus of dictionary already stored in the service. Right, so that's a threshold that you're dropping, and then now all this you drop. Another kind is if you want to customize your own. So remember, this video is a custom data, right? So if you want, you can put your custom vocabulary that you have found, like Boto tree, Amazon. So in this video is someone speaking about a demonstration of a product, right? You can actually hear what she said and then add to that. Add some words that is not in the general language, right, into the data. All right, so you play one round of the video, right? Remember, you play one round of the video and listen to what is being said by EC2. EC2 is not a very common dictionary word, right? So you want to put it into your custom dictionary. That's the goal of what you are trying to do, so, right? Okay. So if you have write the custom dictionary, okay, then what you do is feed a custom dictionary into a text file, upload that vocabulary file into S3. Then remember, you can transcribe with telling the tool that you have a vocabulary file URL, right? So you create a vocabulary, and then it will start to retranscribe again, and then use that vocabulary, right? So that should sums up, I hope, a good understanding of how to use the transcription service. Okay, so this is exactly on every start time and end time, okay, to take note of that. Now, a generic question on cosine similarity on words embeddings, right, to identify the matching target. The answer is yes, right? How we know whether two words spoken are the same? One common method is calculate the cosine similarity scores. All right, that's one very common method. Okay, and if you can calculate the entire cosine similarity scores for every single word that is being spoken, right, you should get the overall confidence of the file. But because these two, let's assume you are using these two. Remember, you have a scores that have the least of confidence scores. In essence, if you aggregate that scores, you also get the full accuracy of this transcribed file. Okay, but if you are doing your own bespoke model, that's something that you have to build. So how did the scores get calculated is, in essence, using accuracy, right? You can use cosine similarity for it, okay, on the words that you have predicted. Okay. So that is how you see a full transcription with every single start time, okay, as it flows through the video, what you are predicting. The accuracy is, in a way, still pretty reliable, right? How can it be so low? Think about it, right? Okay, you might want to play the video and hear it, right, when you do your own data to see whether it's exactly as low as it is. Okay, and sometimes it's because the pronunciation and the muffling of the words, okay, can be affected as well. So that is the key. Okay, so that should sums up the transcription example using the video key, right? So feel free to do some another one other than cosine similarity is using the word, right? Word is ground truth, right? So word error rate. So this is saying I want to find accuracy, okay, but find how many words has been sort of not done correctly. So this one you have to use a library called Jiwa. Jiwa, you have to say, like, for example, hello world and hello duck, right? It's only 50% because hello is correct. What world and duck is two different. So you can tell one is 0.5, right? Because hello is the same, but world and duck is different. One thing to know, I didn't go in depth, is if you are doing with text, you have to lowercase it. You just have to make sure all these nuances are resolved. Otherwise, the words may appear different, but actually it's just like capitalized or whether a misspelling. Then you call it, you see that it's different. That's not a very good way to do it, right? So that's something that you want. So you just transcribe it, right? Then you can print out that the baseline word before using is 5.18. So the word after is 2.62. Okay, so the percentage change actually much drop lower, right? So actually the custom vocabularies reduce the sort of similarity between the words itself, right? So that's the key message here. So you can try that. So for the testing results, right, out of the sample is the one they use to train, right? Okay, it's also dropping, but it's dropping less, okay? So that's the key. So we can summarize this in sample and out sample of the data. Okay, baseline was this before custom vocabulary. Then after that you drop, right? So you might not want to use so much of a custom vocabulary in that sense, right? Okay, so that's something. Other kinds of common tools are blazing text. Okay, that's also one kind of metrics that can be used. All right, that hopefully for text, those that should be transcription driven. Okay, hope that you can. Now you also can appreciate by now to a certain extent after going through deep learning. Deep learning is very different from data science and machine learning. Is that it requires a bit of engineering effort, right? You need to be able to build an architecture of the model. If you are as an engineer to train, you might also need to be able to even connect to service to deploy. So it's not as straightforward as just using models and calculating errors. Okay, so that's something that you might want to take note of the key difference there. Okay. Now, next is the service called poly, right? So just now was speech to text. Now let's reverse the situation. It's poly to speech, right? So if you are lonely, you can talk to poly. It's very common today. You see virtual agents, okay, and sometimes you can choose the speech, who's to speak it, right? Okay, this goes in the field of NLG. Actually, you may heard of NLP. There's NLU, which is to understand meanings, and there's also NLG. So each one are different. Okay, so generation is almost like the music generation. So just now we covered using LSTM to do music generation, right? So I'm generating classical country disco music, okay, getting the data from the files, okay, processing the data, loading into tensor, okay, then training with LSTM here, right? The module, quite standard architecture, just need to repeat itself, okay, and then training on the Adam optimizer or loss function, then be able to generate the data coming out of the generation, all right? So let's say if you don't want, you want to use a service, okay, like Poly. So how do you do it? Yeah, you should not look at my, okay, can. So right, imagine this, okay, you tell it this is a sample text to be synthesized, this is test, test, test. All right, so use Poly client, right? After you call the S3 service, then the ID JoAnna is the one that you use. Okay, this one is a documentation, check out on it, and then you'll be able to find it. Right? Then the S3 bucket to store the data after you generate, okay, then synthesize. All right, okay, so if you synthesize this, you should be able to get this, right, speech, okay, then you can download, right? So I can share this in the Zoom chat. You guys can download and play with it and see the quality and accuracy of it. So that's very straightforward Poly. You just have to put the text in. So imagine after you transcribe just now, right? What can you do? You send the entire transcribed words into this Poly client. Then it will print out the speech for you. So can you see the interchangeability of these two tools together? So that's Poly for converting text to speech. All right. Now, text to speech, speech to text. What about understanding, right? So if I want to understand, it's text to meaning, right? That's where comprehend comes in, okay? So comprehend is where I want to do what I did just now, right? Beginning a sentiment analysis like Keras, right? So I'm doing things like language detection, keyword extraction, okay, meaning from text, NLP, all it, right? So that is the field of it, okay? Which can be plenty of, okay? Now, comprehend takes a long time to train. And that's something that the job, okay? So what you do is, okay, you can basically put any data that you can collect, right? From social media, web page, etc. So just need to load it in, okay? Then get, again, tweet, right? I'm using tweet, okay? Sentiments of positive, negative, neutral. So these are the one of the data. So I'm going to use this sample tweet, right? It's going to use comprehend, assessing comprehend client, okay, detect key phrases. So I can print out the phrases, right? Okay, let's see whether it is still here, okay? So let's run it, okay? Okay, so key phrases here, you see score, okay, 9986, okay, the confidence of that phrase, right? Okay, a great day is a key phrase, right? My equestrian knowledge, good use, work. So a phrase is 1 word to 7 words. So each one is basically a score of a phrase. Okay, so that's basically phrase. Entities is what are the nouns that are available. Organization will be AWS. Okay, title will be peculiar for the tweet. Okay, you can see this tweet is basically it was a great day when I can randomly do good use, right? So these hash are basically okay. Let's try this, right? If you do this, okay, yes, it performs name entity recognition. Correct. Yes. Okay, even Singapore found in the text is it. Okay, you change the capitalization, it still works. Okay, so actually capitalization shouldn't affect the detection of comprehension. Okay, now if you use API, let's not look at the API key again. You just have to take API key and the secret, right? Okay, so that should be something you need to do. Okay, can then install Tweepy. Okay, it says some tweets, right? So basically, these are all the tweets you pull in from the web. There are always two ways to get data, right? As a deep learning engineer, you either scrape data or you use API. Okay, two fast way, right? So this is using an API. You have to apply for an account for that, otherwise you can get banned or whatever, right? But anyway, otherwise you do scripting. So you can see user description is basically what the profile, location, even in this language, right? Okay, so I'm going to extract post, timestamp, locations, sentiments, positive, negative, neutral. Okay, okay, find the text, find where is it. Now, every tweet is in a dictionary, if you can tell. So actually in the dictionary, it does have information like the location, etc. You don't have to analyze the text. Analyzing a text is just to get the sentiments, all right? So you append your sentiments, right? Negative, positive, or neutral. Okay, data frame is to organize it. So these are the results. So you can see that tweets at a certain location at a certain timestamp, the sentiment is positive. Because it's prediction, right? So remember, it's a softmax at the end, right? So you have all of them should add up to a probability of 1. So positive score confidence with negative score with neutral, you add up, it should be equal to 1. All right, so that's the basis of this argument. All right, so the advantage of using comprehend is this language is being learned. And I don't actually know how accurate it is, but let's try, okay? So yeah, it's actually pretty accurate, right? I'm looking forward to the next. Now imagine you do your own custom model. What happens is, right, you have to build one for English, one for Arabic, one for Chinese. You get the point? Yeah. So yeah, the language is identified automatically by the tool itself. Remember, one of the feature is to do language detection. So yes, there is a way to do it. You need another model for that, right? Or at least a dictionary for that. All right. So multilingual terms definitely can be multilingual. Assuming you mean like combination of two language together. Maybe like Malay to Mandarin, right? Correct. Yeah. Uh, challenging. I would say challenging. You can try out. I haven't tested, so I don't know how effective the service will be. But it's much more challenging, right? Because it's like mixing language together. So, but if you have trained it, right? Remember, language detection, you have to train a model to learn it, right? The main way. So, yeah, correct. So, different APIs they might depend, right? So, I wouldn't say I haven't tried it for Amazon service. You can play with it and see what's the result, right? So, another way is just to look at the location. I wouldn't think this gives you any very good insights also, but it just means it could mean that the people in Singapore, Scotland are very positive people, right? It need not mean that the tweet message is positive. It just means they are very positive people. So sometimes you just check, but this is just to show you how you can use comprehension service, all right? So comprehension service are still in general quite common, okay? In a lot of main use case that should be a key. All right, next would be something along the part of hash thread. All right, now image to text. So we saw speech to text, text to speech, text to meaning. One most common is image to text. Remember, there are two main models you to discuss under deep learning, right? To know that, to say yourself you understand deep learning means you understand there are two main models. One's a convolutional for image mainly, one's recurrent mainly for text, for speech, for language, right? If you understand these two means the two data, image data and text data, you sort of appreciate them, right? At least you have a basic understanding of it. So that would then sort of complete your foundation in deep learning to even say that you understand what deep learning is, right? So these are the most common use case, right? Not that they are the only use case, right? So text extraction beyond a simple optical character recognition. So traditionally, it's simply using this technology, OCR, right? Now it's trying to extract meanings, okay? More advanced models are even trying to figure out whether this part of a text is related to another part of the text. So sometimes you need augmented technologies to go and improve, okay? So that's a key to think of. In essence, if you can convert text to speech, speech to text, image to text, text to image, right? Image to text like captioning also, right? Not just in detecting the text written, that is actually very high level, right? So let's see if I can recall where's the test track. Okay. New, this is still okay. Now, so here, right, test track. Okay, so I'm going to do custom entity detection, right, with test track and comprehension. So I'm going to use test track to sort of take an image and get some data. Okay, so we are using a public data set from Kaggle, right, which is like resume entities for NER. Okay, so this data set contains candidate resumes, right? You guys know what's a resume. So I'm extracting data from resumes. Imagine this deploying on a HR's problem. You basically can screen people, right? Okay, yeah, of how they are coming, right? Apologies on that. Let me open it. Okay. TQDM is just a workflow process of a tool. Okay, everything SageMaker, Proto3, all these are here. Okay, I'm using TestRec using name entity recognition. Okay, so I upload my resumes. Okay, using TestRec. Okay, I extract the PDF files. Okay, so it will just submit into the job, right? So I just have to make sure I put the functions. Okay, process two files for now. Okay, rename the PDF to text. Okay, write the output to a text file. All right, so in progress, that should be how it is. Okay, next will be this upload the text output to S3. Okay, that should be key. Okay, now Amazon ground truth labeling. This is where you do some labeling, but we are not going to do that so much, right? Okay. Next, comprehend. Okay. After I have extracted the text, okay, and I'm skipping labeling. Labeling means you have to do custom labels, right? Okay. But now you can use comprehension to read it. This one takes a while to train, right? As mentioned. So after it's trained, right, basically you have to find the precision of the score in understanding the message, which is 73, 78, and 75 for half one. Okay, then you upload the test PDF resumes to S3 again. All right, so performing using test rect. Okay, upload the data for inference. Okay, that is basically it. All right, so that's a few jobs that you do. For the entities of the job completed, and that should be it. If you print the results, basically you can see that for every resumes, you're extracting the key skills, right? Okay, confidence, this guy has analytical and problem solving skills. He has AWS skills. Solution is a skills. All right, you may not think that solution is a skills, but anyway, these are the top few, right? Printing out. Okay, for a few lines for one document. So I'm trying to extract the document too. Now, image to text is one of the more challenging problems. It has been hard to always get a very good accuracy. So you can feel free that if you're excited about this problem, try to solve it. Okay, the confidence score also doesn't seem very trustworthy in this situation, but it's a good try for a few texts. Also depends on the data you feed, right? In this example, we only fed like two data to train, so it may not be that great. And even training two data takes 20 minutes. So that's the situation here. We are using two services. One is to use TextRack to extract the image features, like all the text in the image, right? Then use Comprehend to understand what each text is written in the resumes. All right, so that should be it. Okay, you can. So that's basically the demonstration here in the TextRack to comprehension. All right. Now, comprehension has other interesting tools, right? Okay, so so just now resume is a custom entity. Okay, remember blazing text is trying to do word to vec, right? Okay, generating a vector representation of words in a large corpus, right? Okay, so the resulting vectors is to show semantic relationships. Okay, so this blazing text is one common AWS image library. Actually, you can click here, right? If you click on Amazon SageMaker sample notebooks, right? You should see these few blazing text examples, all right? And this one is slightly different from here, but you can actually explore with all this, okay? But nonetheless, here using blazing text in addition to as an alternative to comprehend, what happens is this, right? Okay, we create word embeddings for the Twitter data set, okay, ingest the data like tweet for telco, set up the training in connect to S3 and the Boto 3 sessions, right? Okay, set the container for blazing text, train the blazing text model to generate word vectors. Now this requires some text mining skills again, as mentioned, right? Like bigrams or n-grams, right? Okay, or skipping grams means skipping words along the way, right? Okay, like 2 grams, 3 grams, provide an efficient implementation of back of words, grouping a few words together, okay, to really understand the relationship between words in the data, right? Okay, so that's really for text classification. Okay, like where this text is on which layer, so CPU, GPU, and you can use all these. So set up it, okay, this one is a C5 container, okay, so take note of the instance, right? It helps you to train the volume size, the match run, and the input file. Set the parameters for it, right? Skipping grams, epoch is 5 minimum count, threshold, learning rate. So you see all this is almost like your neural network, right? Your learning rate, you have to set, your sampling threshold, you have set, epoch, you have to set to train the model. So blazing text is a model, right? That you are trying to do word to vec, right? So a SageMaker, right? Put the train data, pour it, then start training the data, right? After you train the data, what you get is the model and the vectors, because you're converting text into vectors, right? Okay, so you can draw visualizations. So these are all the words that you have collected. And what's a vector means that, right? You are trying to get the relationship of the words, not so much of like a word count, like how many times they're being mentioned, but more of the sort of peer-to-peer relationship, right? It's like at and in are very close, you know? Okay, your, our are very close, right? Sometimes you say your, our, pronouns very close, right? iPhone upgrade very close, you see? At website very close. So actually what this word to vec is measuring distance relationship between words, which is pretty advanced, right? I'm trying to learn the relationship between words, all right? Sometimes the words can sort of duplicate their comma, their exclamation. This means you have not cleaned the data. So we didn't really clean the data, right? We straight away just throw the data into the SageMaker modeling, right? So that's quite lazy way of do so, but it's just for demonstration. So take note of data processing step is important, right? Nonetheless. Okay, so that's something that you do. You can use other libraries to fetch your data. So that's blazing text. You can use the algorithm, okay, with the sort of deep learning algorithm on SageMaker, right? Can connect to it. Okay, hope that clarifies the summary of all the text data. Okay, lastly, last example I would like to show is forecast, which I talked about. And here I'm going to show more of the DeepAR algorithm by within AWS itself, right? You can obviously use other algos, right? Stochastic models, the ARIMA, or even Prophet by Facebook, these are all possible. But nonetheless, let's take a look at the Okay, forecast. Okay, so forecast is basically time series data, right? So you just have to get forecast DeepAR. Okay, the container, the program for it. Put frequency here is predicting hours, 48 time hour ahead, right? Okay, then time zero, when is the start time? So the data starts from this period. Okay, 24-hour period is 24 hours is considered one period. This is how the time series data can look like originally from 2016 in June. Okay, so this is time series data. Okay, the example here is the data is basically a frequency of events. Okay, random generate data points. Okay, so you can cut the data into training and testing. Training is basically the first few parts. Testing is basically the last few parts. All right. So this is the key main difference there. Okay. So train the model, SageMaker, right? Okay, C4 is this demo, right? Okay. Take note the C family that if I recall correctly doesn't have GPU, but it's fine. Okay. For here, the data size is small. So epoch again, remember mini batch size, learning rate, dropout rate. So DeepAR is LSTM RNN deep learning model at the back end, right? What you don't do is you don't go in and change the layers, but you still can change the hyperparameters. So if you use the service, you cut one step, right? You cut the step to build the model, but you still should train the hyperparameters, all right? So if you train the hyperparameters, you set the estimator, then you start training, right? Okay, the training will start to run on the test time series. The time series will go by a few epoch. You can check the average loss. So all these are the log data that you are looking at, right? The loss is being calculated. Okay, as it trains, okay, for the few epoch. And let's fast forward all the training, right? Okay, endpoints for inference, right? You create an endpoint, okay, allow people to predict. So set the predictor here, parameters, okay, frequency and the length. Remember, you are trying to forecast a time period for, right? You are predicting, okay, also about quantiles of confidence, right? Like 0.1%, 5%, and 50% and 90%. Samples of hundreds. Okay, so this is how you do prediction. Okay, so if you do back testing, means you test on the past, the target was basically here, right? Okay, the prediction is here. So confidence interval is 80, means plus minus 80, 20% gap, right? Okay. Somehow it looks quite okay to you from a naked eye. Okay, you might want to calculate your accuracy to be more accurate. So different time series, right, comes out with different results. All right. So all of the start point is the same, but I'm just doing with different test data. So for example, you can see the blue shapes are blue line are quite different, right? This is quite different from this. Okay, there's not much noise here, but if you scroll down, right, there's much noise here. Okay, so you realize the more noisy the data, the poorer the model performs, right? The model performs quite poor when there's noisy data. You look at this, right? There's so much noise, but the model just tells you to go up all the way. Not necessarily true, right? So that's a thing that you can improve on, right? So that's how you can visualize the predictions and the results. Right, any clarifications so far? And that should complete the last service I would like to go through today. So we have convert text to speech, speech to text, text to meaning, image to text, and then forecast. All 5 services of AI services you can use, okay, beyond just the bespoke modeling, which we also covered, okay, in general practice, right? And hope that you are able to gain something and continue the competition. Okay, feel free to drop any questions in the Zoom chat if there is. All right.
Thank you so much, Solomon. So if there isn't